So I started off in physics. So I did my undergraduate in physics and did a PhD in medical physics. So I got interested towards the second half of my undergrad, I would say. Was really interested in medical applications. So really enjoyed the kind of the physics, the learning about how the world works, and did my master's project and then my PhD at Oxford University in the MRI department. So my PhD was on trying to be more quantitative about what's going on in the brain. So using MRI scans as a non-invasive method, but rather than just looking at where is something happening. So that's what you normally do with fMRI. It's really good at saying, in this location, something is happening. If you show somebody some faces in a scanner, or if you get them to move their fingers or their legs, you can kind of see which parts of the brain, which localizations are involved in that process. But it's not very good at saying, why is the signal increasing? How much is it increasing by? So we were trying to really quantify, well, actually, what's going on from an oxygen metabolism point of view. How much is the oxygen consumption increasing? How much is the blood flow increasing? How much is the blood volume increasing? So it was really fun. Really enjoyed the science, the kind of learning. How do MRIs work? How can you get more information out of the same hardware? How can you learn more about human physiology as well, both healthy physiology and then what changes in pathology, so what changes in people with Alzheimer's or the earlier stages of neurodegenerative diseases versus healthy aging. And then in theory we were kind of thinking about, well, what would you do for a stroke patient if you could tell whether in a particular area of the brain whether the blood flow is as it should be or not, but then also perhaps even more importantly, whether the oxygen metabolism is still at a healthy level, then that could impact the care pathway and which drugs you're able to give somebody. So that was the thinking behind my PhD. Really enjoyed the research, but I recognised as kind of part of that journey that I was really motivated by the patient impact and being able to work on something that has a good chance of actually ending up in clinical practice and helping people with different health challenges. So instead of staying in academia and looking for a postdoc, I decided I wanted to make that move into industry. I came across TTP and spent several years here really just learning about medical device development and working on quite a range of projects here. A few years ago, together with a couple of colleagues, really to combine my continued interest in how the brain works and how the nervous system works with the really great engineering experience that so many of my colleagues have. And I think universities are a fantastic place for blue skies research or for innovative thinking, for the kind of what if questions, is this possible? What if we could try this? If we do it this different way, what happens? For trying to understand science, understanding the human body, understanding what does healthy aging look like, what do pathologies look like. Certainly historically, I think universities have been about the research and not worrying about the short-term impact. And I think that's one of the things that make them almost unique, and it's kind of what makes them different from industry. Whereas in industry, you're looking at shorter timescales, and you know that to make a company and a product viable in the long term, that there needs to be a return on that investment. You need to be able to make it financially viable, and I think industry is much more experienced, I guess, in how to do that, and I think that transition is difficult, actually, going from a research question in an academic setting where a good outcome is learning something and being able to publish it, to be honest, and even if personal motivations are about helping patients and having an impact, in an academic setting you'd be lucky to have an impact on 10 patients, right? And that's fine. If it's about learning and about understanding, that's not a problem with that. But that's a very different scale to what you're thinking about in terms of making a scalable business. So I think that transition is difficult. It's difficult partly because of finding the right funding sources, and it's also difficult because it's a different mindset that you need to get yourself into. If you've shown that something could work or can work when it's very tightly supervised in an academic setting, that same product, that same hardware may not look like a product ever could, and making something scalable, making something that can be implemented without a without a PhD level person standing next to you helping you use it, that is a different thing. One of the reasons I was so glad to find TTP, where we're still pushing boundaries, we're still doing new things for the first time, but it's in a much more commercial context. So I think in terms of doing a PhD, it suits some people, it doesn't suit everyone. I think it gives you the chance to really deep dive onto something, into a topic that you find interesting, to spend 3 or 4 years really learning about one topic, and doing an experiment, and then that's only the start. Then you kind of look at the data and you go, oh, this kind of makes sense, but now I've got a next question. Why do I see this? What is this about? Well, let me develop another experiment to test that. And you kind of go one step at a time, further and further into the rabbit hole. I love that process. And I think as well, the learning is internal learning in terms of how do you actually read research papers? That's a skill in itself. How do you pick out the relevant information, and how do you develop those experiments? How do you run those? And then, of course, very domain-specific, subject-specific expertise that you develop. I think in a startup, you would be learning about all different aspects of how a business runs very quickly, because you have to. How does the finance work? How does the kind of corporate software work? How does accounting work? How do you meet patients or clinicians or people from whom you get information to check that what you're designing or thinking about actually solves an unmet need, figuring out your value proposition, your product market fit. These are kind of natural words in business, but they're not words that you know when you're coming out of academia. So I think the types of things you learn will be quite different. I expect that the rate at which you're learning can be quite high in either case.
Very true.
Yeah, so one of the things that I find really exciting about neurotechnology is it's an alternative way of interacting with the body compared to pharmaceuticals. So for many decades, drugs have been our go-to solution for any kind of illnesses, from a headache to cancer. And pharmaceuticals interact with your body in a kind of chemical way, biochemistry. And that's great, that works in many, many cases, but not in all cases. And what I find really exciting is that neurotechnology taps into the nervous system, which is kind of the second way the body has to communicate with itself. And I remember learning this in GCSE biology. You've kind of, you've got the chemical, hormonal communications, which are the slightly slower ones. And then you've got the really, really fast electrical impulses through the nervous system. And until recently, there hasn't been much in the way of tapping into that nervous system in order to address health challenges. And I'm really excited about that as an alternative pathway. What excites me is that neurotechnology offers an alternative pathway. Think about pain. The way in which you treat pain with spinal cord stimulation is a completely different mechanism to how you might treat pain with paracetamol, ibuprofen, morphine, with the different pharmaceuticals available. So that's something I find super exciting. And there are so many indications that people are starting to explore in this space. So pacemakers and cochlear implants are the two most commonly used, and then increasingly deep brain stimulation for Parkinson's, spinal cord stimulation for pain relief. I'm not going to pretend there are no side effects in neurotech and in spinal cord stimulation, but it's a very different side effect profile which will suit different people. So I think for me it's about giving patients the choice, the informed choice, and in many cases they're going to try drugs first because you haven't got surgery to go through. Until neurotech becomes less invasive, it's very natural to go to the drugs first, and that's fine, but we know that they don't work for everybody. So having alternatives, I think, is really important. I'm really excited to see what happens in the depression space. There have been some really encouraging, very small studies done in that area with really positive outcomes. Relatively short term at the moment, I think kind of 1 year, maybe 2 years, but for really severe treatment-resistant depression. And by having a deep brain stimulation device implanted, they've had huge, like really sudden, instant changes in their symptoms. I think one of the big challenges there will be scaling that. So figuring out, so for Parkinson's, one of the things that's nice is it's quite understood which part of the brain you need to target in order to get relief of the symptoms. In depression, it seems like different individuals have different networks that have been impacted in the brain, and there are different locations that work better for them. So in a research setting, you can do multiple MRI scans. You can even implant, like kind of short-term implant multiple leads and actually test out within the surgery, what's the impact of stimulating some of these different locations. That's not scalable. You can't turn that into a product and expect every patient and surgeon to go through that process. That's not financially viable for healthcare systems. So I think that's one of the areas that I know companies are working on. I know Abbott is running a big trial at the moment in treatment-resistant depression with deep brain stimulation. So I'm really excited to see the outcomes of that study. And there are also other companies, like Motif is just one example of a company that's doing it's not an implant, but a less invasive brain implant. Again, targeting depression, because I think it's such a widespread condition, and even though a good fraction of people have it under control with medication, there's still a big number of people who do not. So I think that's one really exciting space. Neurotech, by its nature, you're trying to target the right nerves with the right waveforms in order to impact the communication between different parts of the nervous system. And especially in the peripheral nervous system, you have an opportunity to really go for specific organs, specific nerve bundles, and that means that your side effects are also quite localized. I think one of the really, really great things about academia is it's fine to try something risky. And if it doesn't work, it can still be a success. You can still learn something. And ultimately, the end goal in academia, as I see it, is learning. And if you learn that something does work, great. You have a potential new company that you could create, or a potential new product, or a potential new way of treating somebody. If it doesn't work, you've still learned something, and maybe you've learned that it works in certain circumstances, or you've learned that it doesn't work this way, but now you're going to try it a different way. All of that learning is still positive outcomes. Whereas I think in industry, you just have to be a bit more targeted, a bit more thinking about the end outcome, and putting it in a commercial context, which is a little bit different. Yeah, and that's what I love as a scientist in a company of mostly engineers. What I've spent quite a lot of my time doing is needing to really understand what do our clients need from a business perspective, what does success look like for them. Then also really understanding what do the patients need, but not just the patients, what do the surgeons or the clinicians, the people who are actually going to be making the choice or making the recommendation of these devices, what do they need, what's their normal working pattern, how do you fit things in with that, and then really figuring out, okay, so what is it that we're going to ask the engineers to design, because it's not unusual, unfortunately, to spend a lot of time and effort designing something that's not quite right, because you haven't quite got the requirements right, because you haven't quite defined up front what success looks like or what constraints you're working in. So one of the things that I'm really kind of passionate about is understanding up front the mechanism of action as far as you possibly can, certainly as far as you kind of need to understand what makes this therapy work, what are the things that we need to keep in mind while we're designing everything else around it so that we keep that core, and that core doesn't change even while you're making things smaller, easier to use. You're paring back the features because you want it to be simple. You don't need the full flexibility that you needed in academia anymore. You want to make this a simple device, but it still has to work. So I really love that intersection between what's the science, how does this work, but then also how are we going to make it scalable? How can we make it smaller, cheaper, less invasive, while still tapping into that fundamental mechanism so that you can have a financially stable, successful business so that you can then reach the patients and have patient impact. So the first thing I would say is follow your interests. So rather than going for what you think you ought to study, go for the thing that you really enjoy. And to be honest, when I started my physics degree, the bits I was most excited about was astrophysics and particle physics, because they were the extremes. These are things you don't see in the everyday. That was my reason for going for physics instead of engineering, was I wanted to learn about, like, the stars are amazing. How do we even know anything about them? How do we, like, see this? How do we get this information? Same with particle physics. Like, this is fascinating. How does this work? Quantum? What is this? I was fascinated. And then for me personally, during my undergraduate degree, I did those courses. I loved them. But I ticked that box, and I thought, this is great. I have had a chance to kind of dive into this, to learn about this. And for me personally, did I want to spend a lot of time with a microscope, with a microscope in one direction or with a telescope in the other direction, and then doing lots and lots of data science in order to kind of learn a tiny bit more? That wasn't for me. So by the time I reached the end of my undergraduate degree, my biggest interest had shifted from, like, astronomy to medical applications. And I don't think that's unusual to kind of have a bit of a shift as you go. So the thing that stayed with me through that was physics is about learning how the world works and about simplifying things down to a point where you can put it into maths, solve something within some constraints, within some simplifications, and then put that back into the real world context. And my interest in that stayed steady throughout. So if there's something that you kind of really grabs your interest, I would say go for it, because that internal motivation is going to be really important to see it through. If you're still torn between actually like an aspect of this course, an aspect of that course, and if you really want to set yourself up for a career in neurotechnology, by which what I'm thinking of here is the kind of hardware development side. Teams have people from all different backgrounds, and like part of the wonderful thing about that is that you put together the different pieces of the puzzle and the different experiences into one team. But I think the thing that you're always going to need is somebody with an electronics background, because neurotechnology at the end of the day is about interacting with the nervous system through electricity. So I think at a fundamental level, having some experience of that is going to be critical within a team. So something around that electronic engineering or electromechanical engineering, I think, is always going to set you up well. Neuroscience is fascinating, but you'll probably pick up the bits you need as you go. So particularly if you end up focusing in on a particular indication for a particular product, take Parkinson's, being able to do a bit of a deep dive into how does Parkinson's manifest itself, what's going on in that disease. You could probably teach yourself a bit of that, or find the right people to have conversations with to pick up the bits that you need there without necessarily needing to do a full degree in it, in a way that I think picking up a little bit of electronic engineering here and there, I'm not saying it's impossible, but it's a bit harder. And I think one of the cool things these days is you can actually get some of the quite low cost hardware, particularly on the EEG side, to start tinkering at home. So one of the other questions I get is, if I'm a college student, or I'm not even at university yet, I'm a school student, and I want to start dabbling in this space, what can I do? So, well, for a couple of £100 you can buy yourself an open BCI headset. You can get the data off that. You can start looking at how do you clean up the data, how do you denoise it, what algorithms could you put in place. Of course, it's noisy because it's not like a kind of completely medical product, but the barrier to entry has got lower, and there's also data sets online that you can download and play with if that's what you want for implantable devices as well. I think what's really exciting for me is seeing more and more new things coming out of academia but starting to move into industry. So over the last 50 years or so, there has been neurotechnology that's been in industry, that's been in products, but it's been quite limited. You've had maybe 4 products that have existed there, and now I feel like there's this growth in interest, growth in, I think the research has been growing over the last maybe 3 or 4 decades, and I feel like now that research is reaching a maturity level where it's ready. It's ready for people to pick out bits from academia and say, okay, we've spent 20 or 30 years investigating this. This is the bit that we're going to spin out into a company and grow and scale and make accessible to patients. And I feel like that's a super, super exciting time to be at for neurotechnology. So it's not this futuristic, crazy, like blue skies, like crazy thing anymore. But it's still new, it's still exciting, it's still innovative, and being able to, I mean, that's what I'm so excited. That's what I really love about my job here, is it's about helping that transition from research, from from understanding how this works to actually scaling it into a product that can have an impact on patients' lives. So I think it's a really exciting time to be in neurotechnology.